Prepare yourself. We will take you on the journey of a lifetime. 2 lifetimes, actually. The clash between Sir Isaac Newton and Gottfried Liebniz over the creation of calculus was epic. But our story starts long before the two greats collided.
This is Newton's dot notation. So what Newton did was he placed a dot over the dependent variable to show that this was its derivative. Now the reason that he did this was because he expressed most of his derivatives in terms of the independent variable time, which is why he did not need to mention the independent variable. This notation doesn't really apply today because it doesn't work for multivariable calculus, which was a whole new field that developed after Newton's time. Now, the notation that we use today is Leibniz's notation, and it can express calculus in multiple variables. Another form of notation that developed after Newton and Leibniz was Lagrange's prime notation, which defines the derivative in terms of a function. Leibniz's and Lagrange's notations are used interchangeably, and in this presentation we're going to express Newton's notation in terms of Leibniz's, and we're not going to use Lagrange's notation at all because it wasn't around during the time period we're addressing, but it's just a good thing for you guys to know. Now for integration, Newton's notation was particularly unclear because sometimes it was a box and sometimes a line over the dependent variable. First of all, this wasn't clear and it didn't help define the parameters of the integral. Now in Leibniz's notation, you have the limits of the integral a and b, and you have the variable that's being integrated over. This is the notation we still use today, and it's the primary notation for integration because it defines the integral to the greatest extent. Leibniz and Newton had such different notations because they thought about the ideas behind calculus in very different ways. So here's an example of one of the first applications of hyperreals in order to prove something. Leibniz claimed that if there exists a straight line, VA, parallel to the x-axis, and another straight line, BP, which intersects with the same point on the y-axis as VA, but creates an angle theta with the x-axis. Now, if this theta becomes infinitesimally small, Leibniz claims that BP is going to become parallel to VA. So when we get to the fundamental theorem of calculus, both Leibniz and Newton defined it in their own different ways. Now what Leibniz did to define integration was he used the fundamental theorem of calculus. This is not the same version of it that we have today because there were slight modifications made to define it in terms of limits, but Leibniz did use this to define the integral. So Leibniz showed the integral as an elongated s. This was supposed to represent summation. In fact, he actually proved that substituting variables during integration would yield the same results, which is where we get our substitution method in basic integration from. Now, this is called the Leibniz integral rule. However, Newton's applications of integration were valued more because they've impacted physics since the 1700s, which is why we're going to direct our focus towards Newton and his method of integration instead of the way Leibniz developed integration. Now, the reason for this difference in development is that Newton was a physicist, so his aims were directed more at applying calculus than completely defining it. As a result, in his initial use of infinitesimals, he didn't really justify them, which led to a lot of skepticism among his contemporaries. He did define them later, but it may have been some of this insecurity that led him to publish after Leibniz did, which led to the whole controversy. Newton explained calculus primarily in terms of fluents and fluxions. Because he thought of derivatives in terms of time, this turned out to be a pretty narrow definition, which is why the mathematical community prefers Leibniz's terms instead. So a fluxion, which is shown as x dot, is the speed of a changing quantity x. The moment of this fluxion is the amount it increases in an infinitesimally small amount of time t. Therefore, the moment of the fluxion, which is essentially the derivative, will be x plus x dot t.
When Newton found out about Leibniz's publication, he was very angry. Up until Leibniz published his work, neither man had known the other had developed calculus. Newton called plagiarism. In response to Newton's claim, London's Royal Society of Mathematics began an investigation. But Newton was the head of the Royal Society, so Leibniz was found guilty of plagiarism. Leibniz, of course, protested, but it was for naught, and for centuries Newton was regarded as the founder of calculus, while Leibniz waited in the shadows. But time heals all injustices, and history was eventually kind to Leibniz. Seen as his notation was better, more convenient, and preferred by all of continental Europe, eventually even loyal to Newton England came around, and Leibniz is getting credit today. So enjoy the Leibniz notation while doing your Newtonian mechanics.
Okay, so after Newton and Leibniz, there were a lot of incredibly major developments in calculus. There was Euler, and as we mentioned in the notation, Lagrange's prime definition of the derivative. And then there was a lot of progress, and then in the 1900s, mathematicians started to look at the basis of math and define it from the beginning. So what they came up with was the delta-epsilon limit definition, which helped provide a more fundamental and more concrete basis for calculus, because there were a lot of flaws in Newton and Leibniz's ideas of calculus, because they were both defined using very practical concepts which may not apply to like certain exceptions or the complex numbers or certain other things that developed after their time. So we're going to show you the basic delta-epsilon limit definition that most of you probably already know. So the limit of any x tends to a for a function fx will be equal to L. Now, when you're given that epsilon is greater than 0, there exists a delta also greater than 0, and both of these are part of the real numbers, such that if 0 less than modulus x minus a less than delta, then the absolute value of fx minus L will be less than epsilon. Now, we're going to show you the graphical representation of this. Now, if you can remember the way we represented integration the way Newton did it, do you see how this can apply to a much more general function with a lot of irregularities that Newton didn't really account for, because his applications were more based on physics, and that Leibniz didn't really account for because his definitions were based on the idea and the conceptualization of derivatives and calculus rather than a solid mathematical basis. So what we have now as the delta-epsilon definition is like widely accepted. So this is any arbitrary curve, and you'll have a certain point on the curve. I call that A on the x-axis and L on the y-axis. So the point is A comma L. And this is how the infinitesimal change represented by the delta-epsilon limit definition works visually. And now calculus is happy and fun and yay!